So we were going through basics of heat exchangers, and we briefly covered the different types of heat exchangers, right? Like the double pipe, the shell and tube, the plate and frame, the compact heat exchanger, and we focus mainly then on discussing about the geometry of a shell and tube. Um, we went through these equations for delta P, also some heuristics that we are going to revise again when we deal with more details about the heat exchanger design. So the nozzle numbers, and we said that we are going to focus first on getting the overall heat transfer coefficient, right? And adding the Fulling factor to that overall heat transfer coefficient, because previously we checked these equations, like when we're dealing with conduction, we check these equations, right, for the overall heat transfer coefficient based on the inner area and the outer area. But these are considered overall heat transfer coefficients for clean surfaces because we don't have the resistance imposed by the Fulling, right? That we said that is this extra layer that impede heat transfer, right? Because it's bothering the heat transfer area. So we define the overall heat transfer coefficient clean and the overall heat transfer coefficient dirty. And we said that resistances for Fulling, we can have tables to read those resistances, right? And that we typically are going to take the worst value, right? The worst scenario. We design for the worst scenario. And we went through this problem, but it was a kind of long problem because we need to first get all the H values, right, in order to solve for the overall heat transfer coefficient. So we need to recall our equations from internal and external convection to get the H values or convective heat transfer coefficients that we are going to put here in the overall heat transfer coefficient. And then we add the Fulling resistances, right, and check how the overall heat transfer coefficient change. So today we are going to solve a little bit more problems focused on the overall heat transfer coefficient for heat exchangers to gain some practice. And all of these problems are related somehow to our external and internal convection because we have a fluid passing through inside or outside a surface. So let's go through this problem to keep practicing this overall heat transfer coefficient that we said is a very important number, and we have tables in chapter 12 that I shared with you for heat exchangers, and those initial values of the overall heat transfer coefficients help us to do a preliminary design of a heat exchanger. So that's why it's very important to check clearly the overall heat transfer coefficient. So we have hot oil that is going to be cooled in a double pipe contour flow heat exchanger. The copper inner tubes have a diameter of 2 centimeters and negligible thickness. The inner diameter of the outer tube, the shell, is 3 centimeters. Water flows through the tube at a rate of 0.5 kilograms per second, and the oil through the shell or the bigger tube at a rate of 0.8 kilograms per second. Taking the average temperatures of the water and the oil to be 45 and 80 respectively, determine the overall heat transfer coefficient for this heat exchanger. So we need to, again, work on the resistances. And as you can see, everything is pictured in this little image that you have in here, okay? And the first step, well, I come back to this later. The first step would be to get the properties, right? That's our first step always. So we are going to get the properties of the water at the given temperature of 45 Celsius. And we can read this from tables or interpolate from tables: the density, the Brandt, the thermal conductivity, and the kinematic viscosity. We also get the properties of the oil at 80 Celsius. And these are the properties, again, the density, the Brandt, the thermal conductivity, and the kinematic viscosity. In this case, we are going to determine the overall heat transfer coefficient as this approximation: 1 over the convective heat transfer coefficient of the inner area plus the one of the outer area. Why? Well, this can be done. This is a simplification that can be done when the wall thickness of the tube is small and the thermal conductivity of the material is high, because that resistance is not going to impact along your answer. Like last time, you remember when we compare all the resistances in the denominator, we saw which one has the most impact. And if you just count that resistance, the overall heat transfer coefficient is almost the same as if you disregard the other two, right? So that's the case. That's why we can do this simplification. So again, when you have very thin walls made of highly conductive materials like metals, you can do this simplification, okay? Why? Because the thermal resistance of the tube is negligible, or the resistance of the wall is approximately equal to zero. And the inner and outer surfaces of the tube are almost identical, right? Because it's so thin tube. So inner, outer equals the surface area, essentially. Then the overall heat transfer coefficient simplifies as this, where HI and HO are the convection heat transfer coefficients inside and outside the tubes, determined using forced convection correlations, right? The ones that we already revised. So that's the whole explanation to make this simplification. And we can do this because if you reread the problem, the problem says thin wall, a thin wall tube, okay? So that's why we can do this simplification. So as always, we need to start with the Reynolds, right? To determine which region we are dealing with. So I'm going to get the mean velocity of the water to get the Reynolds, because I'm going to use the mean velocity to calculate my Reynolds. So mean velocity is mass flow rate divided by the density and the cross-sectional area of the pipe. What is the cross-sectional area of the pipe? Pi d squared over 4, right? It's a circular cross-sectional area. So zero point 0.5 divided by the density that we read for the water, 990, right? Multiplied by pi d squared over 4. So we have a mean velocity of 1.6 meters per second. We need to get also the hydraulic diameter of the tube, right? Because we are dealing with, remember, we are dealing with a double pipe heat exchanger. So it's a small pipe in a bigger pipe, right? So this one should have a hydraulic diameter because it's not a circular cross-sectional area. It's an annular cross-sectional area, right? So mean velocity times the hydraulic diameter divided by 0.6. So 53.490, which is greater than 400. That means it's turbulent flow, right? If we assume fully developed and a smooth pipe, Vitus-Boetler, right? That's the most common one we have used to approximate Reynolds or high Reynolds numbers, right? So Vitus-Boetler, so that's a big difference with the Vitus-Boetler, right? And it's a highly common use equation that we use a lot in our evaluation of the nozzle numbers for forced convection. So then the nozzle becomes 240.6, DH value 7663. Now we repeat with the oil, right? For the oil, we have the properties written from tables at 80 Celsius, and we need to calculate the hydraulic diameter because we are dealing with the annular area, right? So in this case, the hydraulic diameter is d out minus d in, or diameter out minus diameter in. Why? Well, because I did all the thing here that you can do also. Hydraulic diameter is 4 times cross-sectional area divided by Y perimeter, right? Cross-sectional area 4 pi d out square minus d inner square divided by 4 divided by pi d out plus d inner, right? We cancel this 4, cancel this pi, right? We have here a perfect square that we can develop here, right? And that allow me to cancel this in the denominator. And finally, I have that the hydraulic diameter is d out minus d in, right? So I just put that so you can check that. But essentially, if you have an annular space in a double pipe, you can just take directly this equation, and that's the explanation. So we have the hydraulic diameter. What's next? Again, the mean velocity. Again, the Reynolds. then choose a nozzle correlation. So mean velocity and the Reynolds number for this case. Again, mean velocity, same equation. Mass flow rate divided by density, cross-sectional area. The cross-sectional area is an annular space. Again, so essentially this equation. 1/4 pi d squared, right? But pi d squared is the difference of the big minus the small because it's the annular. So I get 2.39 meters per second. Then with this one, we get the Reynolds, right? Reynolds number with my hydraulic diameter and the mean velocity I calculate and the viscosity I read is 637. It's less than 4K. That means it's laminar, right? So if we assume that we are dealing with fully developed laminar flow, what happened with the nozzle in fully developed laminar flow? It becomes a constant, right? And we have to go to tables to read it. You recall that? That we have a table in your textbook for that? Yes, I'm sure you recall that because we solved a problem. It was our first problem for internal convection. Okay? So again, if the Reynolds is laminar and fully developed, the nozzle becomes a constant, and we go to tables and read the constant nozzle. However, the tables in your textbook are for a circular cross-sectional area, right? And I don't think your book contains annular because remember we are in the oil side and the oil goes through the annular section, not the circular section. In the circular section, the water is coming in, right? And in the annular is the oil. So we have this correlation for nozzle for fully laminar flow in an annulus. 7.2, this I took from another textbook, but if not, it seems it's in your textbook too, 7.2. So in order to read this table, we need to get the ratio of the inner and outer diameter. So if you do that diameter, so inner divided by outer diameter is 0.02 divided by 0.03 is 0.6. So that means I'm between 0.5 and 1. So you need to interpolate. So you need to interpolate to get the nozzles at 0.667. That is the ratio of the inner to outer. And after interpolation, I got 5.545. So in this other textbook, I got 5.45 for the nozzles on the tube side of the annular space NUI. Have in this table, if you see, let me show you my table. This is from another textbook, okay? But it appears similar in your textbook. So NUI is the nozzle number for heat flow at the inner surface, only with the outer surface insulated. And NUO is the nozzle number for heat flow at the outer surface with the inner surface insulated. We are reading NUI, right? Because it's in the inner surface. We are evaluating. So imagine the water is here in the little circular cross-sectional area. The oil comes here in the annular area, right? So it's the inner, assuming that the outer is insulated because the heat transfer is occurring between this area, right? The water and the oil enclosed in the annular. So NUI is the one that we are reading. So again, this is something to recall then. Then H comes out of the nozzles like we always do, right? Important, for all the annular space, you plot all the time the hydraulic diameter. Okay, here again. Common mistake, 75.2 is going to be H for the annular space. And the overall heat transfer coefficient for this heat exchanger is just 1 over the sum of the inverse of these two overall heat transfer coefficients. Why? Because this is a thin wall, right, tube. So we can disregard the wall effect, right, or the very small resistance imposed by the wall. Why? Because it's very thin and we are We are considering that this pipe is made of a highly conductive material such as metal, right? So note, you compare now these two values, right? Here, note that the overall heat transfer coefficient is approximately equal to the value of HO, right? Just check these two numbers, 7.74.5 versus 75.2, right? Um, in this case, since HI is much bigger than HO, or the inner convective heat transfer coefficient is much higher than the outer. This shows that the overall heat transfer coefficient in a heat exchanger is dominated by the smaller heat transfer coefficient when the difference between two is very large. To improve the overall heat transfer coefficient and this heat transfer in this heat exchanger, we can apply some enhancement techniques such as fin surfaces. And that's what we said when we evaluate fins, remember? Because if you evaluate Newton's cooling law, Q equals overall heat transfer coefficient area delta T in this case, what is the most easy thing to change? Is the area. The temperature is kind of difficult because you will have certain entrance, right? They are going to tell you, you need to add this heat exchanger to this process line. So they cannot change the process line just for you to enter at the temperature you want the heat exchanger, right? So most typical and most cheap thing to do also is to add fin surfaces. So again, as you can see, it's very important that you have handy and recall all your internal and external convection nozzle numbers or correlations for the nozzle, because we need them to calculate the heat transfer coefficients for the overall heat transfer coefficient.